This is Magnetism 5. So we saw in our last video the flux equation, which was equal to B times A times cosine of theta. Now this equation assumed that the field is uniform over the area of the loop, but we can calculate the flux in a non-uniform field, one where the field strength actually changes from one edge of the loop to the other. In order for us to do this, we actually need to use our integral, which means we're going to be summing up all the fluxes through every small bit of area. So we can see how that applies to this situation, where we're asked to calculate the magnetic flux from the current in a long straight wire. Now we know that our magnetic field decreases as we move away from a wire, so that's how our magnetic flux is also going to be changing. So we can start with our equation. Again, our magnetic flux is not going to be a constant, and it's actually going to be changing with respect to how far we are away from our current, with the equation mu naught I over 2 pi r. Again, where r is the distance away from the current. Now we know our area is just going to be A times B, but our flux changes with respect to A. So we can replace dA with B, which is a constant, times my change in A, which changes with respect to r. So I can make that substitution back into my equation. And you can see all my variables are constants except for the r, so I can pull all of them out. And I'm left with the integral of dr over r, which we know to be natural log. Where my distance r is going to change, according to my picture, from C, which is where my flux starts, at the beginning of this loop, all the way until C plus A, the distance from here to here. So then my final equation looks like the natural log of C plus A over C, which gives me the magnetic flux from the current in a long straight wire. Now we're going to look at Ampere's law, which helps us to solve for the magnetic field, just like Gauss's law helped to solve for the electric field whenever we had situations with high symmetry. So, whenever a total current I passes through an area bounded by a closed curve, the line integral of the magnetic field around the curve is represented by this equation here. Again, ds is just going to represent a line of length in this case, and for most of the situations it's going to be L. So, anywhere the magnetic field is perpendicular to our line integral, it's just going to be equal to 0. And any time that they're in the same direction, then it's going to be equal to B times L. So we can see how that applies to solving for the magnetic field inside a current-carrying wire. So here we have a wire of radius r that carries a current I, and we're asked to find the magnetic field inside of the wire. So starting with our equation, if we are looking inside of the wire, then the current is not the total current, but a portion of the current. So just like we looked at current density, we're going to look at current density here. So the current that passes through a certain area, which in this case is going to be pi r squared, has to be equal to the total current passing through the total area. You can see that the pi's will cancel out, and we're going to be left with our current through our area equal to r squared over capital R squared times I. So that means that we can replace our I through with r squared over capital R squared times I. Now, for this area or this closed integral path, our magnetic field is going to be the same at all points, so that can be pulled out of the integral. our line integral is going to simply be the path of this entire outer portion. So that becomes 2 pi r. In this case, L is equal to 2 pi r. And then we can finally just simplify our equation to get magnetic field by itself, so that we get magnetic field is equal to, well, here one of our r's is going to cancel, so that gives us mu naught I r over 2 pi r squared. So again, this is our magnetic field inside of a current carrying wire. Now we know what our magnetic field is outside of a current carrying wire. So you can see that when R is equal to capital R, we actually get this situation here, where R is equal to capital R. We can replace that, and then you can see some of those R's are going to cancel out. So inside of the wire, it's going to increase like our graph we see here, and then decrease with respect to 1 over R as we move away from our wire. Now we're going to solve for the magnetic fields inside of a solenoid. Again, a solenoid is just a series of coils piled up together, so when a current runs through it, a magnetic field is produced on the inside. Now an ideal solenoid would actually have a magnetic field of 0 outside of the coils, so that only we have magnetic fields on the inside of the coils. So again, starting with our equation, here we need to choose our ds so that they are in the same direction as my magnetic field. So if I chose it so that it was coming out of the page, if I chose ds to come out of the page, then you would see that they'd be perpendicular, and we said that that would be equal to 0. So we need to choose our ds so that it's in the same direction as B. If that's true, then our magnetic field is going to be constant at all points. Our ds is just going to be L, the length of the solenoid, and our current is just going to be the current that's actually running through the wires. But we need to multiply that by however many number of coils we actually have. So, for the magnetic field of a solenoid, it's simply B is equal to mu naught times N times I over L. Now we can see how all of this applies to inductance. We've said before that if we have no current, we have no magnetic field. So in this situation, if we close the switch and we have an increase in our current, we're going to have an increase in our magnetic field, which means it's going to then create an induced EMF. This effect is called self-inductance because a change in flux through the circuit and the resultant induced EMF all arise from the circuit itself. That means that a coil of wire, or a solenoid, which is seen in this symbol up here, can be used in a circuit to store energy in the magnetic field. This is called inductance, which is going to be represented by an L. And it is a ratio of the flux to current. Now, this inductance is very similar to capacitance, the ability to store charge, per unit of voltage. So again, they're going to be very similar. For an inductance, the unit is going to be a Henry, which is a capital H. This comes from flux over current. Remember, flux has units of Tesla times meters squared, and current has units of amps. Now we can use the information that we just derived at the beginning of this video to help us solve for the inductance of a solenoid. So we said that inductance is going to be our magnetic flux over our current. Well, remember that for a solenoid, we have to times the magnetic flux for one coil times the number of coils. And magnetic flux is just magnetic field times area. And now we can use the equation for a magnetic field inside of a solenoid to replace B. And then you can see that our current is actually going to cancel out. So we're going to be left with N squared mu naught A over L. And this is the inductance of a solenoid. Now, a couple of things happen when you have inductance across an inductor. Here we have a picture showing a steady current in the left side of this inductor. The solenoid's magnetic field passes through the coils, establishing a flux, which you can recall comes from the right-hand rule with the curling fingers. Now we're going to look at a slightly different situation. What if we now have an increasing current? Well, then we have an increasing flux. Now again, the flux produced from this current is in this direction. So then we're going to have an induced current that's going to oppose this increase in flux. So in order for us to oppose this increase in flux, then we have to have an induced magnetic field go in the opposite direction. That induced magnetic field will then produce an induced current opposite the direction of the current in the solenoid. So now that we have this induced current, we're going to have an induced EMF, which can be calculated using this equation here. Again, that depends on the current. And this negative tells us that the potential or the induced EMF must be opposite what's happening with the current. And we'll see two examples here. This particular induced EMF causes it to carry positive charge carriers to the left and establishes a potential difference across the inductor, meaning we're going to have positive on this side, negative on this side. Now we look at the situation with decreasing current. Remember that our magnetic field was still going to the left, but now because we have a decreasing current, we're going to have a decreasing flux. So Lenz's law says that we're going to oppose that decreasing flux. So the induced field will also be in that direction. If the magnetic field is in that direction, then we are going to produce an induced current in the same direction as the current of the solenoid. So that means if I put a negative here for a decrease in current, that negative times this negative means I'm going to get a positive change in potential as I move across my inductor. So that means on the left-hand side, I'm going to have a negative potential, and on the right-hand side, I'll have a positive potential. Here's a good summary of what we just talked about. On the left-hand side, you see a resistor. Now, resistors always have a decrease in potential, like we saw in circuits. For inductors, you will have a decrease in potential if the current is increasing, but an increase in potential if the current is decreasing. And finally, if we can calculate a potential difference for an inductor, then we can calculate the power dissipated through that inductor using this equation here, which is still a combination of IV. But now our current is still there, but our V was negative LdI dt. And we can also calculate the energy stored within these inductors using this bottom equation here. Again, you can see the similarities between the potential energy stored within an inductor compared to the energy stored in a capacitor.